All right, guys, so let's get started. So I think before the break, we started working on the design of a shaft, no? Okay, so I don't have those notes, but I mean, maybe you can remind me here. So before the break, we're working on, I'm guessing, shaft design. Okay, so basically a shaft, you know, something like this. So basically, what is the main function of a shaft? Is to basically transfer power, no? Let's say from an engine to different components. So the first thing I defined was power. Okay, so what is power is work over time. I mean, this is like a quick review. Maybe I'm going to give you even some extra details. So what is work? Work by definition, you have work for something that's moving in translation. Generally, you know that is force times distance, no? Okay? But now, what is the similar stuff for something that is moving in rotation? So for something that's moving in rotation, the force is equivalent to what? To the moment. And the distance should be equivalent to what? To the change in angle. Does that make sense? All right. So change in angle, so if you think about it, it should be then moments around torque, because it will be a torque instead of a moment, times the change in angle, let's say d theta, and the amount of time will be what? Dt. So you know that the angular velocity, the definition is d theta dt. So really, I think I give you the equation that the power will be equal to what? T. So the torque times the angular velocity of the shaft. All right, they are even more detailed, but then probably yes. So then, what is the maximum loading? So for example, what is the maximum stress in something moving in shear? So sorry, in something moving in rotation, I'll give you the answer, will be shear. So basically, if you twist something, it's going to break due to shear, and we know that shear due to torque or to a torque will be equal to what is given by the equation TR over J. But this will be different than if you have shear due to a vertical force. Now you have vertical force, this should be equal to what? Tau is equal to what? VQ over IT, no? But again, this is not for torque. This is just for a vertical force, for shear force. All right? All right, so basically, I think these are the two basic equations. Maybe we did one extra one. So, yeah. So basically, you see what that both of these equations have the torque. No? Okay. So if you wanted to do the design, all right, so you can combine the two equations. So combining two equations, we're going to have, so for example, from P equals T omega, you can find that the torque will be equal to the power divided by the angular velocity. And now if you substitute over here, you're going to have what? P divided by omega times R over J. And I think how we wrote this, there's no different ways when you look at it. Yeah, so basically on one side, what depends on the geometry. Okay, I think I wrote that equation here. The last, I don't know if this is the last equation, but basically I tell you this, what is this side? This side is only based on geometry. And this one will be based on loading, but as well on the material. So we can know what is the maximum shear stress for the material, so you can determine what is the maximum power depending on the geometry that you can apply to the structure. Now, vice versa, knowing the power and knowing what is the maximum stress of your material, you can find what should be the appropriate cross section. All right. Okay. But we say, I think I discussed at the end, probably I told you this, I don't remember, that this is a problem that most of the people, yes, most of the people will start over here when designing a shaft. But what is important when you do a shaft? Let's say you have a shaft with different gears attached to it. It will be attached through, let's say you have a gear. What is important over here between the contact of the shaft and the gear is that there is no slip, no? So when this is a contact with another shaft, let's say, the shaft is not going to start slipping. So basically, what we need to define is the angle of twist. So basically, what I was saying the other day, probably, if you base your design solely on this, okay, probably you're going to find out that the best shape for a given shear stress will be a tube. Okay, did we discuss that? Okay, so it will be a tube because when you look at this equation here, what should be the maximum shear? It should only be at the end of the shaft of the tube, no? Okay, not really at the center. So you look at this, you only need the material over here. But then what happens if you have a tube with the wall not being thick enough? It can maybe resist in shear, but what's going to happen when it's going to be applying to the force? It's going to start twisting, no? And if it starts twisting, then what's going to happen to the connection between, let's say, the two gears, between the two gears here? You're going to have slippage. So you're going to lose a amount of power that can be transferred, correct? Okay. So what's important also as well is to check the angle of twist. And I think over here, the last thing we read is that the angle of twist. So, okay, so for a uniform cross section, I think I gave you the equation. Yes, you have angle of twist equals to TL over GJ. Yeah, so I think that's what we did before the break. Okay. So now I'm just going to add one thing for this. So for a non uniform cross section, so this will mean that let's say we have something that is thicker initially. And then you have another one. So in that case, the angle of twist is the summation. So in this case would be I to N, but in this case, N will be 2 of T sub I, L sub I. This can be different materials, so on. So basically, if this is twisting, let's say, Phi1, and this is will be twisting Phi2, at the end, what should be the deformation? Should be Phi1 plus Phi2, no? Okay, so let's go up here the summation. Okay, so all these equations, I cannot guarantee that, but they should not be new to you. You should have seen them in solid mechanics. No? In this class, what I'm going to do is maybe do some more specific application. Okay, so I have here an example. So let's say example over here. All right, so let's say you have an engine over here. Which needs to this shaft is ridiculously big, but it's connected to a shaft to a generator. Okay, so this is your tube, okay, connecting it. And you know that the length, so let me put here. Okay, this will be your tube, which you know has a length L, well, L will be 2 meters. You know this shaft is rotating at 80 radians per second. Okay, and has to transfer a power of 32 kilowatts. Okay, so what they're asking you here is to determine the thickness of the tube so that the maximum shear for that material is 140 megapascals, and that you want your angle of twist to be equal or lower to 0.05 radians. So let's see, is it better with light or no light? Yes, what's your question? Let me know to the left, so maybe I need to go to my right. Will I help?
Yes, that's very perfect.
Okay. Yeah, let me know those things, guys, okay? Again, that's too far for me to see how it is. And here, the screen is not set up properly, so. All right, so this is what we have. So we can do the same thing as before, and then we'll substitute at the end if you want, okay? So let's just be repetitive, okay? I don't want you to memorize one equation, but you can rederive it every single time. So we know the definition, what is the power, is what? Torque times angular velocity. What is shear for something in torque would be TR divided by the moment of inertia, okay? So again, if we combine these two equations, all right? So in this case, we have T, we need to find R. So we know the power. See. Let's see, what do we need to solve for? We know P, we don't know T, so we need to remove T. Okay. So from the first equation, from here we can find that T. Okay, so from here we can find the same thing as before. We can write this, and T will be equal to what? T divided by the angular velocity. It's R divided by J. J, I like to call it J personally, but some people call this I sub P, which is the inertia. And the equation of this one, I'm going to look at it in function of the diameter. So, okay, so in function of the diameter is pi over 32. Outside diameter to the power 4 minus inside diameter to the power 4. Okay, so if you write everything in function of diameter, it will be easier. Here should be equal to what? Side diameter divided by 2. Okay, so let me try to combine these two equations over here. Basically, we'll have what? We'll have should be equal to P divided by angular velocity. D outside divided by 2 divided by pi over 32. D outside to the 4th and it's D inside to the 4th. So okay, I forgot to put some data over here for the problem. Okay, it's not that important, but basically we know the material of this will be A36 steel, for which G, we're going to need that for the angle of twist, is 80 gigapascals. Okay, I also forgot to put something here. We don't know we need to find the thickness, but we know that the outside diameter is 40 millimeters. Okay, so basically that will mean that now from this equation, we need to solve for the insides. So let's see, this will give you what? Okay, let's do some basic algebra. I'm not going to go too fast. Okay, this will give you what? If we move this one to this side, we have tan of D outside to the 4th minus D inside diameter to the 4th will be equal to 32 power over this times D sub naught divided by 2 divided by pi. Okay. I'm not going to go too fast, so it will give you outside to the power 4 minus inside to the power 4 should be equal to what? 16 D outside divided by pi divided by the shear, so that finally we can find that the inside diameter to the power 4. Omega. I forgot the omega divided, no? Thank you. So the inside, I'm moving this one to this side and the one to the other side will be D outside to the 4th. So I'm first moving this one to this side if you want, and then I move this one to the other side. Will be the inside will be equal to what? D outside minus 16 P D outside divided by pi tau omega. I mean, I'm going to leave it to, yeah, I think we can just go here. Let's see if I have here the solution, the value. Yeah, so if you solve this for what data? So what was the data we had for P equal 32 kilowatts? So you need to do what? It should be 32 10 to the 3. D sub naught we say was 40 millimeters. So that would be what? 0.04 meters. Omega was given to us to be 80 radians per second. And what else do we need? Yeah, the maximum shear for that material we say should not exceed, so 140, 10 to the 6 pascals. So if you do the substitution of all this data over here, and you take the root to the power 4, if I'm not confused, it should give you that the inside diameter should be 0.0375 meters, which is approximately what? 37.5 millimeters. Okay, so we can say the wall thickness of the tube. I know after doing all these assignments, you know this, but this sometimes you do the mistake for a factor of 2, and is so it will be the outside, this will be the inside. So what will be the thickness? So if you do the outside minus the inside, what would that give you? Will that give you the thickness? It will give you twice the thickness, and that's a mistake. So basically, T will be the outside minus the inside divided by 2, which gives you a wall thickness of 1.25 millimeters. Okay, so any questions so far? All right, so like I said before, and this is generally a problem that is commonly done, okay, and in real life, all right, is that they stop the design over here. They say, okay, everything is fine, but this is only based on the shear, okay? So the next thing you need to do is what? You need to check or verify, if you want, whatever you want to call it, the angle of twist. So in this case, this is a uniform cross section, okay? Shaft or bar. So your tablet is which one?
Oh, this is Lenovo Yoga. It's about to die though.
Okay. It's gonna what?
It's about to die though. It's not gonna be.
Oh, okay. All right, so basically is this. So basically what we say was the expression for the angle of twist is T and GJ. Okay, so all right, so over here we're going to do the reverse over here. So here we find T, then T over here using the equation we had over here. All right, T we say will also be equal to power divided by angular velocity. So we could say this would be equal to P divided by angular velocity times L divided by G, which is the, instead of modulus of elasticity, is modulus of elasticity before torsion. This one we say is pi over 32, d outside to the 4th minus d inside to the 4th. So we can come over here. Let's say, so this should be equal to what? So we can write phi, let's do as before. Let's move this one to that side, d outside to the 4th minus d inside to the 4th will be equal to what? 32. Can you see? What? No? 32. Moving the 30 to the top, so power times divided by G pi, and that's it, no? Yeah. Omega. And omega, again, I forgot. Keep forgetting that omega. Thank you again. So now we can have over here d outside to the fourth minus d inside to the fourth will be equal to 32 p times L divided by G pi omega p. I want to go to the next page. Next page, I'm going to leave that one still. You can still do this one again. You're going to do this. So now from this one, we're going to find that d inside to the fourth is equal to what? Will be equal to d outside to the fourth minus 32p times L divided by G pi omega phi. And just do as before. We know D outside, I wrote it before, is 0.04 meters. We know P is 32 10 to the 3 watts. Is that the same as before? Omega is 80 radians per second. And this time, what do we need? G, we just wrote it down, is 80, 10 to the 9 pascals, and phi, the angle for our design should not exceed 0.05 radians. So if you plug this data over here, it gives you that the inside would be equal to 0.06889 meters, which this is approximately 0.0, let's say 27. No, it goes by 26889. I'm rewriting the same thing, sorry. I wanted to write over here. This will be approximately 26.889 centimeters. So again, if we do now T, so as before,
It'd be 26 millimeters.
Millimeters, sorry, correct. 26 millimeters. So as before, we have T will be D outside minus the inside divided by 2. And this is going to give you that this approximately will give you 6.6 millimeters. All of them. But basically what we have is that if we base design on, let's say, on the material, so let's say design it's only on shear, this gives us that T was approximately should be 1.25 millimeters. If we do the design based on the angle of twist, this gives us what? T equals 6.6 millimeters. So this is a very good example. So which one is here? Which one of these two is controlling the design over here? The maximum shear or the angle of twist? So this should be the angle of twist because it's more pessimistic. So you can say that this one is the one that controls the design, no? So now you see very well what will be the issue if you just don't go and change the angle of twist. This one will be perfectly safe, but look at the difference in thickness. It's 4 times, no? There's a factor of 4 between one and the other, or even more. All right. So if you only base your design on this equation here, I mean the one we derived before, you only base it on I think I'll put it here, but if you only base it, okay. If you only base the design on this equation here, you might think it's safe, but what will happen with the angle of twist? You will have a lot of slippage, no? And probably one of the gears will end up, at least one of the teeth of the gears probably will end up failing. I mean, you tell me. So which one will you use? The thicker one or the thinner one?
Well, I think I think it's just better to find it off the angles.
I mean, from this point, yes. Okay.
I mean, is that on?
What happens is that if you have a multiple, you know, one shaft that made a different cross sections, it might change, you know. But everything will be the same material. But let's say in general, we could say that if you base your design on the angle of twist, it will be more conservative.
Okay.
Because it's more pessimistic. All right. Okay, so let's see what we can do next. Oh yeah. Okay. Okay, so now we have done the basic shaft design. All right. The next thing we're going to look at it is at, so we know a shaft by itself. All right. The shaft by itself is useless. Okay, all right. What are you going to do if you're not transferring power? But if you wanted to transfer power, this is something we're going to do later. But what should you? How do you connect a gear to a shaft? I think somebody mentioned that the other day. You have keys, no? Over here, you have keys. Okay. Did you guys take? What's the name of the course? ME304 before going to this class? So did you look at this stuff?
Yeah, but we didn't do this. We just talk about keys.
So what did you do in that class?
You tell me. I don't know. Yeah, I have a screwdriver.
Yeah. And 10.
Yeah, there you go.
Made a box out of 10 and riveted it. We welded on a sheet of plate steel.
So the riveting, welding?
Just manufacturing press.
But not really.
It's freaking out here.
Yeah, I was about to say
You learn lots of nuts and bolts.
Yeah.
difference between hammers.
Socket and cat screw.
Whatever. Let's not. I'm not gonna get involved. So studying the class, you will be introduced to the way to connect different stuff to different components, maybe the manufacturer. I mean, personally, that's not one thing about it. I think should be dedicated about how do you take a model, whether you use CATIA or SolidWorks.
SolidWorks, exactly.
Okay, so you take SolidWorks or CATIA model, and then you can try to look at the assembly. And the assembly, let's say, for example, you need to design a shaft with different gears. You need to create all those components within the drawing, no? And look at the tolerances, and then basically, I mean, whatever. I mean, to do this stuff, then you need to do from the CATIA model to the G code now for manufacturing. That's not what you do?
That would be a good way to teach the class.
But that's not what you do?
They touch on G code, but they don't really go in depth.
Okay, I mean, whatever. We're not going to resolve the issue here, no, not in 5 minutes. But anyway, you have keys. So something we're going to do next, but if you want to think about it, I cannot give you an introduction. Now, the keys, if you think about stresses, are the keys going to help or they're going to be detrimental to the stresses? Are they going to increase or decrease the stresses, in other words? Increase, no, because of the sharp edges, no? Yeah,
that's right.
So basically, you know, if you need to do this one, Sally, a simple calculation would be just you calculate the stress and say instead of saying it would be this whole cross section resisting the load, you can just say it will be the internal one, no? Okay, but all this stuff generally is managed by using what is called concentration factors. That we'll cover later on. Okay, it's the same thing as if you have a plate or a beam that is full, and then let's say you make a hole inside. is not gonna have the same resistance for the normal stress, no? Okay, anyway, this is a key. But here, so next thing we're gonna be doing is one, looking at the connection of this, actually that will be two, but one, what I really wanna look at is what happens when you're gonna connect one gear to another one. Yeah, so for example, I mean, it's hard to do, but generally you will have okay, so here will be here you have forces and moments. So basically, the next thing we're going to be looking is this first. What are the forces between the connection of two gears, and then also what will be the different stresses due to the keys or to the holes that might be in your design. So this section will be loads. Loads on a. I call it shaft, even though they might, as you can see, it might be a tube. It's because every time I hear the term tube, to me it's not related to power. If you hear a shaft, to me it's always related to transfer power, no? That's why I like to use the, if you want, you can have solid shaft or hollow shaft, but I like to use the term shaft. All right? So over here, what would be the general loads? So what loads? Can be applied to a shaft. And let's say we have a shaft over here that is supported, let's say here on one end, the pole, and so it's rotating between these two. What type of loads can be subjected to this? You can have what? You could, if you want, you can have, to make it complicated, you can have distributed load. You can have punctual loads. Obviously, you can have a torque. No? You can have the forces here of the reactions, and so on and so on. Okay, let's just do a general case. So let's say you have all these different loading. So all these different loads, what kind of stresses are we going to induce on the shaft? Okay, shear stresses. But let's say we have shear stresses due to torque. I mean, that's the one we just based. So it will be tau equals TR over J. But you could also have what? Shear stresses. Due to, because let's say all this stuff has a weight, or you can apply forces due to bending. And if it's due to bending, what will be the equation? dq over IT. And if there is bending, what does that mean? You can also have bending stress. That should be equal to what? I mean, let's just do the simple equation. We know it can be more than one, but it will be, let's say, M1, or let's say MC over I, instead of 1I, MC over I. I mean, you should know what this means, no? Let's say, I mean, let's just do the more general case. Let's say you can also have axial stress, which also will be on the same direction as the bending, which should be equal to what? Okay, so obviously this is the worst case scenario. All right, you can have all this stuff. All right. We're gonna go, like I mentioned, to the forces on gears. So basically we have here one gear, Maybe do a little bit bigger. That should be a little bit bigger. I'm not that good at doing this. So first, one thing, and I mean, this is common sense. It's not that complicated. If this gear is going clockwise, so what does that mean? That the tooth over here is going to try to push this one, the lower gear, in what direction? Counterclockwise, no? Otherwise, this cannot work, all right? So I'm not very good at doing pictures, but let's try over here. Okay, so let's say, obviously there is tooth or different teeth gears. So let's say that when you apply over here, the force, it will be, we can break this force into a radial force, and let's say a tangential force. So if I put it over here, this figure, this will be, if you want, the radial force that goes to the center, and now this will be the tangential force. Okay, so I need to do another figure, but so leave some space. So over here we have omega sub t will be the tangential force. Omega, W sub R will be the radial force. Okay, and you're gonna have one W sub N that we're gonna call the normal force. And that's the figure I need to do. So basically, let's say we have here, I'm not really good at doing these figures. So let's say this will be a tooth on the gear going to the center. So this will be gear tooth. All right. So if we look at this one, so let's say in that tooth, you're gonna have obviously it's not going to be good my figure, but this would be a tangential. You can have, let's say, a radial of this one, but in what direction should be the real force being applied on the tooth? It should be like normal to the surface, no? Okay. So really the real force being applied to the tooth will be the normal. And angle between the normal, if you want, and the tangential, we call it phi. So maybe it was not a good notation what I used before. So in here, phi is what is known as the pressure angle. Okay, so if you want, let me just do here a different figure. So we have here WR, here would be D. Make it clear, okay? This would be over here, WN, and this is the angle phi. Okay, so from basic trigonometry, you find that the tangent of the angle of pressure or the angle of pitch will be equal to what? Will be equal to the WR, so opposite side divided by WT, or you can find then the relation. I mean, whatever, and what could be the other one? You can find that, let's say, cosine phi will be equal to what? Cosine phi will be equal then to omega t divided by the omega n. I mean, you can find different relations, but let's say you have this two over here. Okay, so now this is the important part here. We have a question. So the torque T produced by the gear. Yeah, sorry. Thank you. So the torque T produced by the gear is what? What will be the torque? So you have the gear here. The torque should be equal to what? Force times distance, no? Yeah. So I'm going to do the easy one. Distance should be what? Radius, or let's say diameter divided by 2, no? So now the question is over here. Which one really will be producing the torque? WT, WN, WR? WT. Okay, which should be the tangential, no? Yeah, so it should be this one, WT. That's correct. So basically, this should be equal then to WT times R if you want, or WT times D over 2. All right, so now, next. Recalling that we know the power equals to TW, so again, that's going to mean that T is equal to the power divided by the angular velocity. We can have what? We're going to have that T equal P divided by omega will be equal to will be equal to WT. And let's use the diameters, okay? Times D divided by 2. So from this expression, we can find, let's say, that the tangential force, if you want to transfer a certain amount of power, the tangential force should be equal to 2P. 2P divided by omega times D. Yeah, sorry for that. What happens is that it hits here the projector. So that's why I cannot move it, okay? It's not, I'm limited, okay? That's probably another good thing for the tablet now. Yes.
So for the tangential force, you have it acting like a perpendicular to the radius, right?
Yes, what happened is that really, I didn't want to do, but maybe here's this figure here, you say, no, it's confusing you a little bit. Should be really, the W2 should be tangential here, normal to this direction, and then the normal will be something in the middle.
So I guess the normal isn't necessarily acting parallel to the recurve.
No, correct. So if you want that figure, it cannot be randomly, but it should be more, really want to do correct. This should be your, if you want your coordinate system for this one. So to be accurate, I just did that way to simplify. This should be your WR. This should be your WT. Can you see the figure? Oh, no. See, I'm sketching nothing. This should really be your WT. This should be your reference frame, no? Going in the radial direction towards the center of the gear, and then this should be really your mega sub n. So that figure is not really that good. I was just trying to do a general one. Really will be this way for each one of the different tools. So the one that really clearing you see here, the torque will be this one WT. That will be perpendicular to the direction, no? For the one at the center. That's what I thought. When I did the figure, I saw that one of them very accurate. Okay, so basically what does that mean is that now, let's say you do the design, the basic design of a shaft, like we did before. Okay, with the two equations, you check the angle of twist. And now you want to attach gears to the shaft. Okay. So based on this one, they said you know what is the amount of torque, you know the diameter. So now you can define what will be the amount of the force T that's going to be applied into the tool. You can have a gear for which some you will have each here will have a testing that will give you the resistance of the force for each one of the gears. I mean, it's more complicated than we're gonna go. So, for example, if you're gonna look at the rating of gears, do you think you can put any number of T on either one of them, or do they have to be a certain combination? There's a certain combination based on the ratio, no? Okay, so it's not that you can put anything. So basically, once you know level this, you can go and select the couple of gears that you want to find, no? Materials, thickness of the tooth, because the manufacturer will give you the WT, WR, or WN, okay? For each one of the different gears. But again, this is just kind of an example because there is multiple different types of gears, okay? Generally in cars, for the transmission, there are what? Helical gears, no? Okay, so obviously you will have different types to have the forces that are being applied. Okay, and you have multiple different types of gears. Okay, so it's just to show you that you need to think about those different things. Right, so all right, so let's see next. Looks like I will write the same equation in different units over here. Okay, yeah, this is not important. I don't even know if I'm going to do it. Okay. All right, so generally, this is just change of units. The angular velocity is given in what? Okay, that's a normal, but when you use a machine or in your car, what do you see? When you look at the, at the gauges in your car, do they give you radians per second? They give you RPM, no? So revolution per minute. So basically, when you design a shaft, it's also revolution per minute. So I'm just going to do a change of units here. And generally, the power, powers, yeah, they can give it to you even in kilowatts, but sometimes they can give you that in horsepower, no? Okay, but let's just change this one. So let's just see what would be then omega. So we know omega, the general unit should be radians per second. If we want to move that to revolutions, what do we need to do? So, okay, so we have one revolution, we need to eliminate the radians. So in one revolution, so that means you go once throughout the circle, you have 2 pi radians, no? Okay, and then this one is even easier. Okay, you want revolution per minute, so let's say 1 minute will be how many seconds? 60 seconds. So over here you see now you can cancel the radians, seconds, and you are left with revolutions per minute. So this will mean that if we go to radians per second, so what would that give you? 30 divided by 2. So 30 divided by 5. Okay, to make the units. Revolutions per minute. So basically, we rewrite here the equation WT, the one we just read over here, is equals to 2P divided by omega D. We can write this as 2P divided by 30 of pi D. Sorry, I forgot the omega here. This is just the unit transformation, so 30 over pi omega D. Or sometimes people write this as 2P over ND. Where N will be equal to 30 over pi omega, which is the rotational speed in RPM, revolutions per minute. So I think I can put here, this is RPM, and that's it. Okay, one more thing, I will stop for today. So now let's look at the power. Power transmitted by gear. So we said before, power is work over time. So this will be what? And we say work will be force and distance over time. So what is distance over time? Okay, so this is velocity. Let's call this one V. Really, we could say here that the power is force times velocity. Okay, what is the value of the force? 18. All right, so the value of the force will be the WT that will be moving at a certain velocity, what? Ft, that if you remember from the analysis, should be equal then to omega times R, that will be D over 2, no? Okay, we could just say that the power over here will be equal to WT times V sub T. Okay, just 2 more lines. There's multiple ways to write this. Basically, this will be V sub t be equal to omega times d over 2. This will be in radians per second, but if we do that in revolutions per minute, what will you have? 30 over pi omega d over 2 now, which would be the same as sine n d over 2. And V sub t is gradually known as the pitch Okay, so for today, I'm going to stop over here, but we still have 5 minutes. Okay, so